Really great. It's a pleasure to have Professor Kotaro Kawai. He is an associate professor in geometry topology group, and he's going to talk about geometry of octonions.
Okay. Thank you for introduction. So first of all, I'd like to thank the organizers for giving me an opportunity to speak here. So it's a great honor for me to speak here in the BIMSA members seminar. So as the title says, today I'll introduce the geometry of octonions. So all of you might have heard about octonions, but first let's review what is octonion and review the say very fundamental properties. So maybe you of course you know that the R, the set of real numbers, and also you might know that of course you know complex numbers, C, the set of, and maybe R or C will be famous, and now H is less famous, and O, octonion, is much less famous. So there are these four guys have many properties, but first, today, let's focus on these two properties. So commutativity and the associativity. So first, let's review our case, the set of real numbers. So of course we know that R is commutative, meaning that A times B is of course B times A for real numbers. And also the real numbers are also associative. So associativity means that this equality holds. So we first multiply B and C and then multiply A. So this is equal to the right hand side. So multiply A and B, and then after that we multiply C. And of course, in the case of R, these two are the same. So associativity holds. And next, the case is a C, the set of complex numbers. And again, as we know, these are commutative, and also they are associative. Yes, so these are two famous cases. And the next case is less famous. So the H, the set of quaternions. So in fact, quaternions known to be non-commutative. So A and B not necessary, A times B not necessary, B times A. So the commutativity is not necessarily hold. But still associativity hold for quaternions. So now today's main topic, octonions, has no property of both. So they are octonions, not commutative, and associative. So from this table, so octonions might seem very strange at first glance. But today I want to say that this non-commutativity and the non-associativity actually give rise to some very interesting geometry. So in this sense, I really love this geometry. So now I want to explain why it is interesting. So anyway, the multiplication of octonion doesn't have a good property. So and one reason is that it can be expressed in a nice way. So first let me write down this multiplication on octonion say in a nice way. The nice in this meaning. So in fact we can describe the multiplication of octonion nice way in this sense. So to describe the multiplication of octonion, first we describe octonion in this way. So octonion is a R8 as a vector space. So we decompose octonions into the real part and the imaginary part. So real O plus imaginary O. So as a vector space, it is a real R and R7. So the multiplication of real part is just a very standard multiplication. So just the multiplication of real numbers. So there's no interesting information for the R part. So the interesting information contained in the imaginary part. So the multiplication on imaginary part is the essential to understand the multiplication of octonions. So in fact, now we have this fact. So that is the multiplication of octanion is in fact described by certain 3 form on R7. R7 means the imaginary part of octanions. So the meaning is that the multiplication of octanion is described by 3 form is given by this table. So multiplication is an operation that generates 1 vector from 2 vectors. So if we have 2 input, if we have a 2 vector field, we should get the 1 vector field. But we can do this if we have the 3 form. Say, so for example, indeed we can explicitly do this. So if we have 2 vectors, u and v, but for simplicity we assume that they are perpendicular. So then we can take the contraction or take the interior product. So phi 0 and uv. So we get the 1 form, but taking the metric dual, we get the 1 vector. So in this sense, in fact, the multiplication of octanion is in fact described by certain 3 form. So this 3 form is really nice. So in this sense, we can encode the information of the multiplication of octanion into the certain 3 form on R7. So now let me define one Lie group, so-called Z2. So now Z2, Lie group Z2 is simply defined by the automorphism group of octanions, meaning that it's a set of GLO, so that is a linear isomorphism O, and it preserves the multiplication of octanions. And as I said, the information of the multiplication is encoded into the 3 form. So in fact, it is equal to this group. So the set of GL7R preserving this 3 form, phi 0. And it is known that it is a subgroup of SO7, so special orthogonal group of dimension 7. So in this way, so from the octanion multiplication, we get the Lie group G2. And in fact, this Lie group Z2 is a really nice one, so in this sense. So in fact, it is a compact and simply connected and simple Lie group, and which is a 14-dimensional. Yes. And also, I do not explain phi 0, but in fact, we can describe this phi 0 in, say, very explicit way. So one way is one of the nice ways to decompose R7 into R and R6. So here, of course, R6 is considered as a C3. So in this case, this phi 0 can be described in this way. Here, this X is a coordinate on the first R, and omega 0, and the capital omega 0 is given by these guys. So this small omega 0 is, in fact, the standard Kähler form on C3. And this capital omega 0 is, again, the standard holomorphic volume form. So then, in fact, from this description, it is really easy to see that the Lie group SU3 is contained in Z2. So in this sense, so Z2, Lie group Z2 is actually closely related to the Lie group SU3. So maybe I will review this point of view later. But at least from this very simple description, we can see the inclusion from SU3 into Z2. And also, now we have 3 from phi 0. And so then, in fact, we can define, say, nice subspace of R7. So for example, if we take the 3-dimensional subspace, say, written by A3, and now it is called associative if the associativity holds on the 3-dimensional plane. So as I said, the octanion are not necessarily associative, but now we can define a new guy, associative subspace, by requiring that the associativity holds on the 3 plane. So in fact, this part is a little bit non-trivial, but in fact, in terms of 3 from phi, of this phi should be phi 0. So, so in terms of this phi 0, in fact, the associativity conditions can be described in this way. Yes, so the volume A is, let's say, standard volume form induced on A. So, yes. So maybe if you know the calibrated geometry, so in fact, this will define a calibrated submanifold. But anyway, and also anyway, by requiring the associativity on the 3 plane, we can define the associative subspace. And also similarly, we can define the co-associative subspace. So meaning that its orthogonal complement is associative. So in this sense, we add co-associative. Yeah, but just this is not so important today. But anyway, by the break of associativity, so we can get a new geometry.
Is it because it's like quaternion part, like three-dimensional, like the projective quaternion? Where did 3 come from? Why 3?
Oh, why so 3? Well, why this? You mean why this is 3-dimensional?
Why not 3 plus 4 and none of like 2 plus 5?
How to say? Oh.
Yeah, that's what I want.
So maybe.
Okay, we can talk about later.
Okay. So in other words, associative plane, there is a 3 plane that is invariant under the, say, a kind of cross product multiplications. So then in that reason, maybe submanifold this should be 3-dimensional. Oh, okay. Yeah. I hope this is okay. So now this is a, say, theory for vector space level. So in fact, we can consider it, say, manifold version very easily. So by just requiring that they are pointwise same. Okay, so the meaning is this. So first so now we can consider it a manifold version. And to consider this, so we should start from a 7-dimensional manifold. And also we should start from the 3 manifold on a 7 manifold. Okay. So then in this case, in this situation, we can consider the pair, so 7 manifold with a 3 form. This is we call that this is a manifold with a D2 structure if this condition is satisfied. So for each point of x in M, we have this identification. So the tangent space at x with the phi at x is in fact can be identified with R7 with a standard phi 0. Yeah. So anyway, pointwisely, it is a standard one. Then it is a manifold with a D2 structure. And so then we can define, say, associative subspace into, say, manifold level. So then, in fact, the 3-dimensional subspace is associative if its tangent space is associative for each point of x in sigma 3. Okay, anyway, they are pointwisely associative, so it is associative submanifold. But now here we want, but this is say, but up to now there's completely the same at the linear algebraic level. But now here we want to add a more structure. So that is, if the manifold with the D2 structure satisfies a certain integrability conditions. So today I will not explain what it is. But in this case, so this 7 manifold with the 3 from 5 is called the D2 manifold. Maybe I'll mention about the integrability condition later. But still, if you know, say, some complex geometry, so the manifold with the D2 structure is a kind of almost complex manifold. And then this D2 manifold is like the complex manifold or even Kähler manifold. Yeah, something like that.
you assuming n is minimum 1?
Uh-huh. So
Is m minimum 1?
maybe, for phi induces, in fact, a metric. Yeah, maybe I will explain that in next slide. Yeah, so thank you for that. Yeah, in fact, yes, so now, up to now, we only have the 3 form phi, but in fact, it is a part of Riemannian manifold that I will explain next slide. But if we have the integrability condition, then in fact, the associative submanifold have a really nice property. So in fact, it is known to be a calibrated submanifold. So it's a minimal submanifold, in fact. Okay, so these are, anyway, we can define manifold with a data structure and associative subspace, associative submanifold, and the D2 manifold in that way. So anyway, these are, say, very basic definitions. So now I want to explain that why these are interesting. Yes. Yes, okay. So anyway, maybe from the beginning, maybe this geometry looks, say, strange, somewhat, because octonions are strange. And now I want to explain why these are interesting. So again, first let's go back to the linear algebraic level. So now I want to explain why it is interesting. So in fact, now I feel that this G2 geometry is interesting even at the linear algebraic level. Yes, because since, as I explained, the associativity does not hold for octonions. But this is in fact a really interesting part, because of this, there are many mysterious equations. So now I cannot explain all of these mysterious guys, but now this is one of the candidate, one of the interesting equations, interesting or mysterious equations. So for this equation, so if we have two vectors, so u and v, then we have this equation. Here I means the interior product, so then contracted with phi 0, and then take the wedge products with IV phi 0, and again we take the wedge product with phi 0. Then so left-hand side looks really complicated, but in fact the conclusion is really, say, simple. So it's just a constant times the in a product of u and v time multiplied by volume of 0. This is a standard volume form on the Euclidean space. So this is a very, say, interesting in fact. And other than this equation, in fact, there are many interesting equations. So in fact, we can often find these mysterious equations by using some representation theory of the compact Lie group of G2. So maybe, so for example, you can check that the left-hand side is in fact will define the, say, G2 equivariant map. Say so we take the u and v, then we consider the map that send u and v to this left-hand side. So in fact, the phi 0 is a G2 invariant. So in fact, it will define the G2 equivariant map. So we might consider the representation theories such as the Schur's lemma or etc. So that we can use these kind of representation theory in an essential way, so that we can find many mysterious equations. So in fact, I like this representation theoretic part. So yes, so actually this. So now I want to say that even at the linear algebraic level, so this geometry is really interesting, I think. And so then let's recall the definition of the manifold with D2 structure. So as I said, the manifold with D2 structure is defined by requiring this condition. So pointwisely, it is equal to the standard one. So this means that the identities on the Euclidean space carry over to the manifold with zeta structure. So then, of course, this equality holds on the manifold. So then this equality actually implies a very, say, important things. In fact, now we only have the 3 form phi 0, but in fact the metric and the volume form are actually induced from this 3 form phi. So again, if you know the Kela geometry, so Kela geometry or something like that, so in the Kela case, this cannot happen. For example, this is like saying that the only Kela form induces the metric and the volume form. So it is not necessarily true because we need the complex structure in that case. But now here, this is a very striking situation that only differential form induces the metric and the volume form. So this is a striking difference, and I think this will be important, but this might cause the problem much more difficult. But still, this is a very, I think, curious property. Okay, so this is about the linear algebraic level. And also let's go back to the, let's go to the D2 manifold case. So as I said, the D2 manifold is a manifold with D2 structure with certain integrability conditions. So now, anyway, I will not give the explicit condition, but in fact, this integrability condition is in fact given by certain nonlinear elliptic PDEs. So now here this says a kind of geometric analysis enters D2 geometry. So in fact, we can study D2 geometry from the viewpoint of geometric analysis. Yes, and also, moreover, this D2 manifold also has a close relation to the theory of a holonomy group. So I will not mention about what is a holonomy group, but it is defined for the Riemannian manifold, and this holonomy group measures how this Riemannian manifold is curved. Yes, very rough explanation of a holonomy group. And in fact, this, say, so-called holonomy group is already classified, say, about actually 70 years ago. And in fact, the existence of D2 manifolds was actually implied by his classification. The classification is 70 years ago. So it's done by Belgier in 70 years ago. So following his result, the holonomy group should be one of these under suitable conditions. So it says SON will be just a generic case. And this UN case is actually corresponding to the Kela case, the Kela manifold. Kela manifold appears here, and the SUN, actually it is corresponding to Calabi-Yau case. So Calabi-Yau manifold appears here. So how to say, so many interesting, important geometry appears in this list. So in fact, D2 or together with spin 7 appears at the end of the list. So in fact, the existence of D2 manifold are also implied by this list, by the classification of Belgier. But in fact, the existence of D2 manifold has long been doubted. So people consider that D2 manifold will not exist, in fact. So in his proof, in the proof of Belgier, he uses a kind of algebraic statement. So he gave some algebraic test. So then these cases, only these guys have survived the test. So, and of course, UN or SUN are very famous. But the people at that time, they didn't know why these guys, D2 say what spin 7 appeared in that list. So that they just survived the algebraic test. And so people don't know that if that manifold really exists. So now his classification is 1955, 70 years ago. And after that, So some people find that the D2 manifold really exists, but it takes 30 years to find the examples. So the first example was found by Bryant, and which was a non-compact one, but it is an incomplete example. And after that, Bryant and Salomon found it a non-compact example, but it's a complete one. And after that, Joyce found the example, compact example. Finally, he could find a compact example in 1996. And after that, some other people found many more examples. Yes. Okay, so now, so D2 geometry is defined in this way. So the manifold with a D2 structure with a certain integrability conditions. So it can be defined a nonlinear elliptic PDE, partial differential equations. And also it can have an interpretation in terms of holonomy groups. Okay. So now, okay, so D2 manifolds also can be understood in that way. So, but now let me explain another, say, important and interesting interpretation of D2 manifolds. So now what I want to say is written in the first diagram. So that is, D2 manifolds are closely related to Calabi-Yau manifold, and also it will be related to a three-dimensional manifold or four-dimensional manifold. So now I want, as we know, these two Calabi-Yau case and Calabi-Yau manifold or three-dimensional or four-dimensional manifold are very well studied. So I hope D2 manifold should be a very interesting one, I think. Okay, so now first let's explain the connection between Calabi-Yau manifold and the D2 manifolds. So as I write here, so D2 manifolds are closely related to the Calabi-Yau manifolds, so SUN case. So indeed, it has D2 manifolds have a very, say, similar property to Calabi-Yau manifolds. For example, D2 manifolds are Riemannian manifold and which are ridge flat, so it has the zero ridge curvature. So just like the Calabi-Yau manifold. And also, if we have the Calabi-Yau 3 manifold, so complex 3-dimensional, so it's real 6-dimensional. So in fact, we can get easily the D2 manifold in a wider sense. Say just multiplying the S1. So S1 times the 6 manifold is in fact a D2 manifold. So in this sense, say we have some examples of a D2 manifold in a wider sense. So maybe in some previously I explained that the SU3 is contained in G2, the group G2 at non-linear algebraic level, but this reflects that fact. So since SU3 is contained in G2, so we can have these examples. So now we want to consider, say, some analysis of Calabi-Yau manifold in the G2 manifold setting. But so we can consider many analyses. For example, we might consider the existence theorem of D2 structure, like Calabi-Yau theorem, say like if the first chunk is 0, then we might get the ridge flat metric, so Calabi-Yau metric or something like that. But so we hope to have the same kind of statement in D2 setting, but still there are not so successful result. And also in the Calabi-Yau setting, there's a famous statement, the famous conjecture, mirror symmetry arising from physics. So some people recently consider the G2 mirror symmetry. So mirror symmetry in D2 setting. So I hope this will be a very interesting interesting problem. And now I emphasize some very, say, similarities to the Calabi-Yau case, but now let me emphasize that there is a striking difference in the D2 setting. So one of the major differences is its dimension. So in fact, D2 manifolds are 7-dimensional. So it's in fact odd dimensional. So I think this is very strange or interesting because all the other well-studied manifolds, such as Kerr manifold or Calabi-Yau manifolds, are all even dimensional. So, but these D2 guys are 7-dimensional. So it looks very, says something odd or something interesting. But I think I hope that there will be a new geometry here. Yeah. Yes. So this is so in this slide I explained the relation between D2 manifolds and Calabi-Yau manifolds. And now I want to explain another direction, so relation to the 3 or 4-dimensional manifolds. So there was such a relation because of these reasons. So in the D2 settings, so on the D2 manifold, so in fact we might be able to consider higher dimensional analogs of the theory of 3 or 4-dimensional manifolds. So very briefly, it can be considered. It can be said as the gauge theory in higher dimensions. So the meaning is roughly this one. So as we know, on a 3-manifold or 4-manifold, we have very non-trivial invariants. So on the 3-manifold, we have the, say, so-called custom invariant by counting flat connections. Or on the 4-manifold, we have a Donaldson invariant by counting ASD connections. So in fact, there is a higher dimensional analog of these two guys, flat connections or ASD connections, so-called D2 instanton. So we might hope to define a kind of enumerative invariant. So count them and to get an invariant of D2 manifolds. Yes, so this is a big dream. And also, as I introduced before, there's also associative submanifolds. And in fact, this is known to be analogous to the pseudo-holomorphic curve in a symplectic manifold. So again, in a symplectic manifold, there's a, say, invariant called Gromov-Witte invariant that counts pseudo-holomorphic curves. So we might, analogously, we might say count associative submanifolds and get some enumerative invariants. And the last one is say very recent one, so-called deformed Donaldson-Thomas connections, or sometimes it is called deformed D2 instanton. So we might hope to count these guys because, in fact, this is known to be the mirror of associative submanifolds. Yes, so associatives can be counted. So analogously, its mirror could be counted. So these are our hopes. And the last one is a very, say, least studied. So in fact, I tried to study this property, some basic property of this DDT connections with my collaborator. So it says it's a mirror of associative submanifolds, but still, before our study, no one knows it is really similar to associative submanifold. But now, with my collaborator, I could show that these DDT connections indeed have similar properties to associative submanifolds, in the sense that of deformation theory, meaning that it's the moduli space is a smooth manifold for generic data structures, or it's minimized a certain functional. Here, functional is a kind of so-called the mirror volume, or dBi action in physics, Dirac-Bonenfeld action.
How many dimensions is DBI?
In fact, dBi can be defined for any dimension.
So that's my question. So DDT minimizes the DBI functional for any D?
I don't know. This is actually this can be defined on a 7-manifold. Yeah, that's just on 7-manifold.
That's what I'm saying. So this is G2 is exceptional 7.
Yeah. Yeah. Yes. Yes. So again, so this DDT minimizes a certain functional. Actually, it's a mirror volume or dBi action, and in fact, the value, its value is given is a topological one, so meaning that it is given by the pairing of a homology group and a cohomology group. So in fact, the associative submanifold have this property. So in fact, we can indeed check the similar property for DDT connections. Okay. So this is a very rough review about our recent result. So then the last slide is say summary. Okay, so now today I want to say what I wanted to say is this. So the geometry of octonions appeared in the title. So now we can call this a G2 geometry. It's in fact interesting, particularly in connection with these points. So first the representation theory at the linear algebraic level, and also in relation to geometric analysis. So we can, in fact, the integrability condition is given by some nonlinear PDE, and also relation to the geometry of a Calabi-Yau manifolds or 3 or 4-dimensional manifolds. Say, in particular, it's a G2 mirror symmetry and gauge theory in higher dimensional, or etc. Yeah, but still, I should admit that G2 manifolds are not so studied. Yeah, so not so many people studied G2 geometry, but as I stated today, I hope D2 geometry is really interesting. And I hope that there will be a great potential for development. Okay, so now I'll stop here. Thank you so much.
Questions?
Does any 7-dimensional G2 manifold bound an 8-dimensional spin 7 manifold?
Sorry. Of course, there are examples of D2 manifold or spin 7 manifold.
An 8-dimensional bound an 8-dimensional spin.
8, yeah. Spin 7 manifold is 8-dimensional.
Yes, I mean an 8-dimensional manifold with a spin 7 structure.
Sorry, you mean the example?
Does any G2 manifold, 7-dimensional G2 manifold bound an 8-dimensional spin 7 manifold?
But bounded, you say bounded.
Yes.
So how to say? So we have talked about it maybe before. So especially so it depends on the definition of G2 manifold. So in the wider sense, of course, we can multiply G2 manifold with some interval, then it is a spin 7 manifold. That satisfies your condition. But no, so not. So sorry, actually, I don't know. Yeah.
So it's a naive question, and I'm sure I'm supposed to know the answer. But so you had this table in the first slide that real, complex, and stuff. So is there anything beyond octonions with other exceptional symmetry, like F4, for example? Can you go further? Like, is there anything? If you really push it, can you think of something beyond octonions?
Maybe R16 or something like that.
Yeah. I mean, could be connected to other exceptional groups like F4.
Maybe there is some say classical results. So it will stop somewhere. So maybe 16 might be possible. But
there's no consensus in community.
But now maybe we should require something. So we require some condition.
There is something called the octonions that are kind of algebra of dimension 16, but no idea of a kind of global geometry.
Yeah, so you need geometry. Like here it's G2.
Yes, so maybe. So if we consider R16, maybe we will lose more properties. So maybe we might get a nice geometry. Yeah.
More questions?
Could you explain why trivial example doesn't exist, like 7-dimensional representation of G2 group? Why it's not example of G2 manifold?
So can I say it again?
So
Could you say it again?
you explained that existence was supposed in 55. First example was in 87, yes? Do I understand you correctly?
No. So sorry.
When you say about Brarer,
Belgium.
Slide
Yeah,
6.
yeah. Oh, yeah, this one.
Does it mean that it's supposed that G2 manifold could exist, yes?
No, this is just a classification result. So I mean that
Classification
Belgium.
of what?
So Belgium gives some algebraic test.
Exactly. Yeah, but it's not example of G2 manifold, yes?
But so yeah, today we know that example. Yeah.
Question: why 7-dimensional representation of G2 group? It's not example of G2 manifold.
Oh, you mean the R7? You mean
I have G2 group, which exponent of G2 algebra, yes?
you mean sorry, I don't know. So D2 is a Lie group.
Then you can construct algebra group like exponential map from the algebra, yes?
So you mean the two consider exponential number? Yeah. So sorry.
More questions?
How did they construct that first example, the juice example? Was it you one them over Calabi feet or what?
So actually, this is not that kind of thing. So it's a kind of say generalization of the Kummer construction in algebraic geometry. So we have the 7 torus, and then say we consider the quotient of some finite group. Then we get some singular manifold. Then after that we consider the say grooving. Then we get to say approximate G2 structure. Then after that we perturb it to get to a genuine holonomy G2 manifold.
Okay, I have one quick question for you.
What about split octonions?
Split octonion.
Is the geometry related?
Oh, so sorry, I don't know it well. Or maybe you know.
So
I think like the imaginary, I mean, like G2 would be like the geometry of the imaginary octonions. So if you consider the imaginary split octonions, I think you have something called G2 stuff that give you a pseudo Riemann.
okay, let me ask you some quick question. You have a Calabi-Yau threefold times circle, that's a G2.
Yeah.
And you're saying that you can count holomorphic curves on Calabi-Yau threefold, and there are many ways of doing that. Shift theoretically, Gromov-Witten theory, Dawson-Thomas theory, there's at least 13 ways of doing it. You're saying if I count those things, I can count associative submanifolds of the G2 given by this Calabi-Yau 3 times circle. Am I right? So
Yes.
curve counting on Calabi-Yau 3 tells me how to count 3-dimensional associative submanifolds of a G2. Is this what you're saying?
In some sense, yeah. So how to say?
I'm going to ask you this later, but is there actually an equation that the partition function of, say, certain partition function, Gromov-Witten, Dawson-Thomas, Pantry-Ponder-Thomas, is equal to count of associative submanifolds? Does this exist?
Actually, there's no such well, still under development. Yeah.
Okay. Let's thank the speaker again.